Welcome all at the Theoretical Computer Science Seminar at Jagiellonian. Our speaker today is Torsten Ueckerdt from Karlsruhe Institute of Technology. You are there for at least 10 years now.
Mm-hmm.
First at mathematical department of KIT and now at the computer science.
Yes.
So Torsten is a good friend of our group in Krakow. We collaborated a lot on various projects, including the product structure theorem for planar graphs, but also a pizza problem, right?
Mm-hmm.
How to eat 4 over 9 of a pizza.
Yes.
I recommend you this paper to read. This was back in Berlin times. Torsten defended his PhD at TU Berlin with Stefan Felsner. Nowadays, I think you are a lot into what page number of planar graphs, planar digraphs.
Mm-hmm. Mm-hmm.
The big question over there is if an acyclic planar digraph has a bounded page number.
Yeah, if it's upward.
Upward, okay. So like
Yes.
planar diagram.
Yes, planar diagram, exactly.
So did you prove it? Is it true?
We are working on it. It's always going one way and the other. Currently, we believe it's false.
Oh, I see. Okay. So it seems that you also have a thing for combinatorial games.
Yes.
Not only eating pizza, but today the talk will be about a variant of a cups and rubber game, a classical game well known in structural graph theory because of its connection to Triwet. So yeah, it's great that you joined us today, and yeah, please start.
Yes, so let's see, let me share my screen. I hope you can see this, and I hope you can also see this pointer.
I see the slides, the pointer, not so much.
No pointer. Wait, then let me start a new share. The screen, there it is. How about this?
Yeah, now you're moving. Are you moving?
Wait.
Yes, perfect.
Okay. All right. So yeah, let's get into this. So thanks, first of all, thanks for the opportunity to speak here, and thanks for inviting me to give this talk. So this is, as Piotrek already said, about cops and rubber, and I want to. So this is a side project kind of thing that I did a couple of times. That I did a couple of times with students here at KIT. So this is mostly based on joint work with Samuel Schneider and Mintuan Ha. Both of them are students who did their bachelor theses on these topics. And Paul Jungeblut, who is my PhD student. So I'm not really an expert in cops and rubber, yeah. I'm just interested in combinatorial games, and this was more a fun thing and something that you can easily give students. All right, so what is it? So let me introduce you to the classical cops and rubber game. So the board of the game is a graph. So this is our graph G, VE. So for instance, this, one of my favorite graphs. And it's a game where players move pieces, and the positions, the possible positions of the pieces are the vertices of the graph. So a piece may sit on a vertex at some point in time. And then you can move your pieces, and the allowed moves are the edges. Yeah, so it's like the vertices are the squares, and then a possible move is an edge. And in this particular game, we have two players. Here it's called player 1 and player 2, but I can also call them the cop player and the rubber player. So the cop player has k pieces, and k is a parameter of the game. So say, for instance, in this little example, it's 2. So he has 2 pieces or k pieces, which are called cops. And the robber player has only one piece. This will never change, and this is called the robber. Yeah, okay, so it's K cops against one robber. And now, how does it work? So they take turns alternately, starting with the cops. So the cops start, and at the beginning, they just place their pieces on the board. So they just place their cops on the vertices of the graph. So here, like this, my two cops are on my graph. There is no restriction where to place them. They can place them anywhere. And then when it's their turn, they can always move a piece along an edge. And since they have several pieces, so in the cop's turn, every cop can move along one edge or stay put where he is. Okay, so it starts by the cops choosing their initial placements. And then the robber sees the board and sees the placement of the cops and picks his initial placement. Say the robber starts at this vertex because the cops are there and there, and also no restriction. He can place himself anywhere. And also when it's the robber's turn, he can move his one piece that he has along an edge, one step along an edge, or stay put where he is. And of course, the goal is that the robbers want, that the cops want to catch the robber. Yeah, that's natural. So he might be a thief or something, and the cops need to arrest him. And for him to be arrested, at least one cop must catch the robber. Okay, so let's make it a little bit more formal. What does it mean? So at any point in time, we have kind of a state of the game. So it's just R is the vertex that is currently occupied by the robber, and this might change. And C is the set of vertices that are currently occupied by cops. And this might also change if cops move. And strictly speaking, this is a multi-set because several cops are also allowed to be on the same vertex at the same time. Okay. And then the cops win if the current robber position is also one of the cops' position. So if, like, on the vertex that is currently the robber, there's also at least one cop. Okay, so then when the state of the game has this property, game is over and cops have won. And the alternative is that we never reach such a position. So the robber can avoid being captured indefinitely. So then the game goes infinitely long, and we say that robber wins by always fleeing indefinitely. Okay, so let's play the game. So here is my two cops. So we started with the cops choosing their positions. Robber sees it, chooses his position. Throughout the game has perfect information, so everybody sees everything, and there's no time limit or any restriction like this. So the cops try to capture the robber, so maybe it's a good idea that they approach him. So they move closer to the robber, one step. Both cops choose to move one step here. And now it's the robber's turn, and the robber wants to flee. So maybe he feels like going there is kind of safer. Okay, now the cops again see where the robber is, and they make such a move. Yeah, so the cop here like feels he's clever, so he wants to prevent that the robber just goes back where he came from, which would be allowed, because if he now would go back where he came from, this cop could immediately catch him, and the game would be over with the cops winning. And this cop is here, so now the robber should not move there into the cop, then he would be caught. Yeah, and the robber should also not stay there because then this cop would catch him. So actually, the robber, seeing the position of these two cops, should decide to move there. Yeah. Now the cops maybe do a little bit of a different thing. So maybe this guy follows him, and this guy just stays there. He's still kind of guarding this vertex, so the robber cannot move onto this vertex. if he wants to avoid being captured. But in this case, the robber still has one safe way to go, namely there. And now maybe the cops do something like this. This cop is guarding this position, this cop is guarding this position, but still the robber could go down here, but actually he could also just stay where he is. Yeah, it's also allowed, he's not threatened. So let's just assume that the robber stays where he is. And now it's the cop's turn again. And the cops maybe do something like this, and the robber can flee there. Actually, this has not been a proof so far, but you can show that on this graph, no matter how the cops try, if the robber is clever enough, he can always evade. He can avoid being captured indefinitely. So this graph is a robber win graph. Okay? And as usual with these combinatorial games, when we have two players, we assume that both players play perfectly. So we assume that both players, they have complete information, they have unlimited time if needed, so they can make arbitrarily complex computations, whatever, and we assume they don't make any mistakes. Yeah. Of course, if the robber is dumb, he just runs into a cop and the cops win on this graph, but still the graph is a robber win graph because there is one strategy for the robber to avoid being captured no matter how clever the cops try to capture him. Yeah. I did not show you the strategy, but it's actually also not so difficult to see it for this. Okay. So under perfect play, for a given graph and a given k, there's always exactly one answer. Either the cops win or the robber wins. Okay, and in this particular graph, with this particular k equal to 2, it's a robber win. Okay, let's change it a bit. So maybe take the same graph, but increase the k. Yeah, now we have 3 cops, which makes the cops better, which should make it easier for the cops to capture the robber. So say now the 3 cops, they start again, place themselves on the board, maybe there, because it's kind of covering a lot of the graph, yeah. The robber knows the rules again, so he chooses his position there, so he should definitely not choose a vertex where a cop is currently and not the neighboring vertex of a cop, so he chooses some vertex that is neither a cop nor a neighbor of a cop. And now it's the cop's turn, they see the robber and they say, do something like this, and we've had this before. The robber cannot go up here, or he will not in optimal play. He will not stay in optimal play. He will not go here in optimal play. He only has one place to go, namely there. And then the cops might do something like this. Again, the robber should not stay because he would be caught by this cop. He should not move onto this cop because this would also make him caught. And he should not go down there because this cop is kind of guarding this vertex as well. Well, so he could go up there, but then this third cop now catches him. Okay. So again, this was just one particular scenario, but you can prove that no matter how hard the robber tries on this particular graph with this particular cops, there is a strategy for 3 cops to always catch the robber, no matter what. Okay. So this, for 3 cops, this is a cop win situation. Okay, so it depends on the graph and it depends on the k, whether the robber wins or the cops win. And of course, if we fix the graph and we vary the k, this is kind of a monotone parameter, yeah? Like if the cops win with k cops, then they also win with k plus 1 cops, yeah? The additional cop cannot make it worse for them, yeah? And similarly, if the robber wins against k cops, then he also wins against fewer than k cops. So it's really the spectrum of possible numbers of cops. So if there's 0 cops, then certainly the robber wins. And well, if the number of cops is like, say, at least the number of vertices in the graph, then certainly the cops win, right? They can just occupy all the vertices and then it's done. So in the spectrum, there is like one turning point where it swaps from robber wins, robber wins, robber wins, to cops win, cop win, cop win. And we decide to call this turning point, so the smallest number of cops that are needed for a cop win, the cop number of the graph. Okay, so this particular graph here, for instance, has cop number 3. Yeah, so 3 cops can capture the robber, but 2 cops cannot, all assuming perfect play. Okay, that's the classical cops and robber game. And what I was interested in is a very particular variant. Yeah, so cops and robber has dozens, hundreds of variants around, including one that is very much connected to Treewits, which I'm not going to mention here. But there was one particular variant which is quite recent and which I learned about and I got interested in it. Okay, and this variant is the following. Oh, sorry. I will give you the variant. First, I want to make sure that you understood the cop number. So say I changed the board. My graph is now a cycle. I don't know how many vertices, some long cycle. My question to you is, do you know what is the cop number of a cycle? Yeah, I see some 2s. And indeed, yes, 2 cops are sufficient to catch the robber and also necessary. 1 cop alone cannot do it if the cycle has length at least 4. Okay, good. Now comes the variant. And the variant is a surrounding variant. Yeah, so the rules of the game are basically the same, just 2 little things. So one thing is that we changed the name. So let me call it the surrounding vertex variant, because there's going to be more variants later. And only the win condition changes. So before, the win condition was that the robber is on the vertex of a cop. And now the cops don't catch the robber by just 1 cop kind of being on the same vertex and like grabbing the robber and arresting him. But instead, the cops should surround the robber. Meaning that they should be on all neighbors occupied by the current robber vertex. So the robber is on some vertex and all the neighbors of this vertex there's cops on there. So instead of in terms of these conditions, the neighborhood of the current robber vertex is a subset of this set of current cops positions. Okay, that's the surrounding variant. And most of what I've said before is the true. So this is a monotone parameter. So there is this turning point where the number of cops is sufficient to surround the robber. And this is denoted as the surrounding vertex variant of the graph. So C sub V, V for vertex. So also there is a surrounding vertex cop number of the cycle, right? Now my question to you is, what do you think? What should this be? Oh yeah, I see some 3s. Very good, very good. Clever people. 3 is indeed enough. And it might be surprising that 2 is not enough, right? So the strategy against 2 cops would be the following. So say the 2 cops start like this, and the robber is there. And then, well, of course, the cops, they want to surround him, so they move closer. But now the robber can just do this. That's allowed, right? So he's not caught. It was nowhere stated that he may not be on the same vertex, so he's not surrounded. So it's not the case that all the neighbors of the current robber positions are occupied by cops. And so now if the cops move further, the robber can continue to do this. Actually, the strategy for the robber against two cops would be to ignore one cop and stay opposite of the other cop always. Yeah. So if the other cop goes clockwise, also go clockwise, and if it goes counterclockwise, also go counterclockwise. And this way you ensure to have some minimum distance to this cop, and this makes you never be surrounded by this cop, yeah, because this cop should have a neighbor of you, so should have distance 1 to you. So if you maintain the minimum distance of at least 2, you will never be surrounded. Okay, and this other cop that you ignored, he alone cannot surround you because every vertex has degree 2. Okay, but it might feel a little bit bad, I don't know, that the robber can be on a cop without being caught. So there's actually also a restricted surrounding variant where you have the additional rule that the robber may not end his turn on a cop. So it means he cannot move directly onto a cop, because then he would then it would be the end of his turn and he would be on a cop, and this is not allowed. But also if he sits at some vertex and the cop moves onto him, he's not caught yet, but he has to move away immediately. He cannot just stay there. Okay. And this is maybe a little bit more natural, yeah? The rest is the same. The goal is still for the cops to surround the robber, just that the robber is restricted in his possible moves. So we get yet another cop number, the restricted surrounding vertex variant cop number, if you will. And I denote it by C sub V, comma R. So the V for vertex variant, the R for restricted. Okay. So now what is my last question to you? No, I promise. So what is the restricted surrounding vertex cop number of a cycle? What do you think? I see some 2s, I see some 3s. Okay, so now it's actually 2. Okay, so I show you how 2 cops can now capture the robber. Okay, so say we're in this situation. So the cops moved there and it's the robber's turn. Now the robber, he cannot move onto the cop. He's not allowed to. So he can stay there or he can move in the other direction. So the cops can come closer to him, approach him, and the robber can again stay there or get away. So if he stays, it's important now that this cop doesn't go on the robber, because this would allow the robber to kind of get by on the other side. So avoid touching the robber, but stay as close as possible to the robber is a strategy which would eventually lead to a surround here. Okay. All right. So this is these variants, and there's going to be more variants. Actually, do you see all the slides? Because somehow my own picture is a little bit in the way, but I think you see it there. Okay.
It's hard to verify if I see everything. Yeah.
Yeah. So my face was occupying parts of the slides, but I think it's only at my end. Okay. Right. So, oh, sorry. Yeah. So we already saw 3 games. Yeah. So the classical game, the vertex variant in surround mode, and the restricted vertex variant in surround mode, and then there's going to be more. But let's first talk a little bit about the 3 variants that we've seen so far. And what I'm particularly interested in is comparing these variants. Yeah. So they are not always the same. Yeah, we've seen the cycle with the classical number being 2, the restricted number, the non-restricted surround number being 3, and the restricted surround number being 2 again. Yeah. So the question is there any connection? And of course there are. So here are some easy observations. First observation is, well, the unrestricted surround variant is at least as, so the COP number is at least the restricted surround variant COP number. Yeah. So the number of COPs that you need in the restricted mode is at most the number of COPs that you need in the unrestricted mode. Of course, because restricting was only restricting the robber. Yeah, we just made it harder for the robber. So it's just easier for the cops. So the number of cops that I need should go down. Yeah. Okay. So it's a trivial inequality. Another trivial inequality is the following. So in the unrestricted variant, there is a trivial lower bound of delta of G, the maximum degree of the graph. Yeah. So the number of cops that you need to surround the robber is at least the maximum degree of the graph, because it would be a valid strategy for the robber to just start the game on a vertex of maximum degree and never move. Yeah. And if the number of cops is less than my current neighbors, I cannot be surrounded on this vertex. It's a very silly game, but yeah. So yeah, for instance, I have here a little graph. So this is just the star, so K of 1 delta, if you will, star with 1 central vertex and delta leaves. In this particular case, delta is 5, where if the robber just stays in the middle, you will never surround him unless you have really 5 cops that occupy all the leaves around the center. So, and you can show that 5 cops are actually also sufficient. So the unrestricted surround cop number of this graph is just delta. However, the restricted variant is just 1, because the 1 cop can just go on the center. And now the robber cannot end his turn on a cop. So he must move away on a leaf where he is immediately surrounded. Okay. So indeed, this restriction might make a huge difference. Yeah, so it might be that, for instance, the star graph has in the restricted case only a cop number of 1, and in the unrestricted case a cop number of delta of maximum degree. So there might be a factor of delta between these things. Actually, you can prove that there's always at most a factor of delta between these two things. So for every graph, the unrestricted surround number is at most the restricted surround number times delta. Let me also give you an idea of this proof. So we have to prove an upper bound on the cop number. So we have to give a strategy for this many cops to always surround the robber. And the number of cops that we have is this. It's delta times the number of cops in an optimal strategy in the restricted thing. So our idea is we mimic this given optimal strategy from the restricted game by saying, for each cop in this strategy, just use a bunch of delta cops that all mimic this 1 cop. So they all stay together as a bunch on 1 vertex and move together across the graph. So now if the game goes on, and then you always look up in the strategy what you do. So if you surround the robber, you're fine. If the robber, however, can now do a move that would be illegal in the restricted version, yeah, because we are now in the unrestricted version. So he might move onto a vertex that is occupied by a cop, or he might end his turn on a vertex that is occupied by a cop. However, in this case, if he ends his turn there, now it's the cop's turn, and the delta cops on this vertex, they can just spread out and surround him. Okay, good. So this shows that always the unrestricted variant is at most delta times the restricted variant. And before I showed you that this is also tight. So sometimes you need to pay this factor of delta. So let me denote this in this table with these arrows. So what does it mean? So I see it as this. So if I have a good strategy here, I can convert it into a strategy here with the same number of cops. And if I have a good strategy here, I can convert it into a strategy here, but I have to pay a factor of delta. At most, maybe. Yeah. So this is my arrow notation. So this arrow here corresponds to this observation, so this inequality, and this arrow here corresponds to this lemma, to this inequality. Okay. Okay, then, of course, there's also this classical thing. So let's also connect this. This is the third observation. The restricted vertex variant is at least the original cop number, and therefore also the unrestricted vertex variant through transitivity is at least the classical cop number. It's basically the thing is, if you can surround the robber, then you can also capture him. Yeah. So you just play the surrounding strategy, and when you're done, you have surrounded him. So either you caught him in between during the play, then you already won, or you surrounded him, and now it's your turn. Then you can just move one vertex and capture him. Yeah. So surrounding is not easier than capturing. Okay. But it's not so clear whether we can draw an arrow in the other way. Yeah? So if you can capture him, can you then also surround him? And this is going to be a question that I'm going to answer today. Okay. Before that, let me first introduce you very briefly more variants, just to give some context. So there's a variant which is called the edge version of the game, where the robber is still moving on vertices as before, but now cops occupy edges. Yeah, so cops are basically play on the line graph of the graph, if you will. So every cop always is on an edge and can move from an edge to an adjacent edge. And the robber is surrounded if the cops occupy all the incident edges to the current robber position. So you can think of the robber being on the crossings of the streets, and the edges are on the streets. And like if you find yourself on a crossing where on all the outgoing streets there are cops, then you are surrounded. Okay. And then there's also, let's maybe play some games. So maybe the robber moves here, and then the cops might do such a move, and now they have surrounded him, yeah, and they would win on this particular graph. There's also a restricted variant where a robber may not traverse an edge that is currently occupied by a cop. It's kind of similar. And then you can you get the respective cop numbers. So the edge surrounding cop number C sub E, and the restricted edge surrounding cop number C sub E, R. Yeah. And then you can again do some comparison of these. So basically the same arguments or similar arguments show you that while going from the unrestricted to the restricted case, you can just copy the strategy. You could just make the robber restricted, so you just an advantage for the cops. And on the other hand, if you go from the restricted cops to the unrestricted version, where now the robber has more freedom, then you need at most a factor of delta for the number of cops, and you can mimic the previous strategy. It's very similar. You can also compare the vertex and the edge version with one another. Yeah, so the first lemma tells you that, okay, when you go from the vertex version to the edge version, you basically have to pay at most a factor of 2. So let me just give you an idea that should sell it to you. So again, you want to find vertex cops given edge cops. And of course, what you do is when you have an edge cop, you mimic it by 2 vertex cops that occupy the endpoints of the corresponding edge. And then you realize if these edge cops surround your robber, then the vertex cops do. So this gives you a factor of 2, which is also sometimes necessary. And on the other hand, if you go from the edge version to the vertex version, then you sometimes have to pay again a factor of delta. And just there's a proof that does this. I'm not going to show it to you. And there's also some constructions that tell you that this is sometimes needed. Yeah, roughly. So somehow all these versions are more or less the same. Yeah, seen from very far, from a rough point of view. In particular, if the maximum degree is small, then they're all more or less the same. Yeah. And but now we have the classical thing, and so far we only made it from all these surrounding variants to the capturing variant. Again, the bottom line being, if you can surround, then you can capture. And the question is does it also go the other way around? So if you can capture, then can you also surround? So the question, and this was asked and conjectured even in 2020, specifically for the restricted edge version, can you prove that the restricted edge cop number is at most the classical cop number times a factor of that? So can you, to the expense of a factor of delta to the number of cops, make capture into surround? Okay. And maybe now it's a good idea to talk about related work and where this all came from. Of course, all these concepts have been introduced by various people. So the classical game is quite old. I think the first reference should be the thesis of Guillot. But more known are Nowakovsky and Winkler for the version with 1 cop, and Eigner and Fromme for the version with several cops, and also the cop number as I defined it to you. And then these surrounding variants, they were both introduced in the restricted setting, the vertex variant by these people and the edge variant by these people. Actually, Komarov and McKay, they are also a subset of the authors here. And I thought also a technical report that never got this paper. Okay. Now, I want to answer this question. I want to show you the solution to this conjecture. And the answer is no. And actually, it breaks in the worst possible way. We prove that there is for every k, there is a graph whose vertex cop number, I don't know, I chose this thing because it's easiest to talk about, is k, but whose classical cop number is just 2, and the maximum degree is just 3. So it's not only that times delta doesn't help you, any function of delta and the classical cop number doesn't help you. Not even delta to the cop number to the cop number factorial. Yeah. It's just the classical cop number can be as low as 2, and the maximum degree can be as low as 3. And still, which might be surprising. And it was also a little bit surprising to us to see this. And yeah, of course, you can ask yourself, so the same thing with cop number 1 doesn't hold, and the same thing with maximum degree 2 doesn't hold. So this is really in the worst possible way. All right. So let me try to give you the idea of how do you construct something where 2 cops are enough to capture the robber, but an enormous number of cops is not enough to surround the robber. So how do you come close to him without surrounding him? Yeah. Okay. And this is going to be the rest of the talk. So here's the rough idea. So we're going to have some gadgets. And this is some part of the graph that I'm going to construct. And it should give you the idea of the phenomenon that is underlying our construction. So assume this is the situation, and assume moreover that we somehow have the robber sitting here. So this is a balanced, complete binary tree, and the same copy here. There's a long path between them, and then in the middle of this long path, there's kind of escape gates to the rest of the graph. Yeah. And no other vertex has some connection to the rest of the graph. The root here, where the 2 cops are currently, assume we're in the situation there's only 2 cops, and we are in the catching, in the classical variant. So 1 cop touching the robber would immediately end the game. So the robber must by fleeing through one of those exit points here in the middle. Yeah. So 1 cop is there that is just behind him, forcing him to make a move. Yeah, if he stays put, he is caught. So he has like someone running behind him. So he must go forward. So he must go down the tree. And the other cop is kind of on the same vertex as the robber in the symmetrical thing. So it's the robber's turn. He makes a move. 1 cop just follows him, and the other one copies the move. So he makes a move. 1 cop follows him, and the other cop copies the move, and so on. Yeah. So he makes a move. So he's forced to go down the tree. He's kind of forced to reveal which exit he's targeting, and with a delay of 1, this cop can copy this move. So at some point, the robber reaches the exit, but with just a delay of 1, this other cop will be at the same vertex and catch him. Yeah, just before it's again the robber's turn that lets him escape. Okay. So assuming the starting configuration, 2 cops are enough to capture the robber here. So why are k cops not enough? So k is going to be kind of the number of leaves in these binary trees. So it's going to be a power of 2. And here it's k equal to 8. So assume that the robber is here. Maybe there's also cops behind him. We're going to move anyways, so I can ignore this. But assume that on the left here, there is no cop, but on the right, there is some number k minus 1, of course. There is exit points. Yeah. Now it's again the robber's turn, and the robber sees where are the k minus 1 cops here. And he kind of needs to make a decision now to go up or down, yeah, to which of the 2 subtrees he wants to go. And he wants to go to the subtree where there is fewer of the cops on the other side. So here it is 3 against 4, so he should go up. So in one of those, since there's k minus 1 cops in total, in one of those there's at most k over 2, or less than k over 2 cops. So in particular, less cops here, then there is valid exit points here. And I maintain this. So now the cops move a little bit. And again, I look at my two subtrees, and where is fewer cops? Like there, now there's a less than k over 4 cops there. And the other cops, they might make some moves. They might here, I don't know, come from the other side and try to get here, but they're not going to be there in time. Or they might go along these paths to, I don't know, do some funny business, but these paths are so long compared to the depths of the tree that this doesn't matter. Yeah. And now, again, the robber can go here, where there is less than k over 8. So in this case, 0 cops on this vertex. And so there might be a cop adjacent to it here, but in the moment that the robber moves there, he is first. He's there quicker than the cop. So in particular, when now the race begins to this exit point, the robber is 1 step ahead and he can escape. Yeah. In order to be surrounded, he cannot be surrounded there, but because in order to be surrounded, there must be a cop there before him or outside before him, and we have to exclude this later. All right. That's the rough idea. So let me show you how to how to make a full construction out of it. So construction of the graph GK. Again, these are the properties that we want. 2 cops should be enough to capture the robber. K cops should not be K minus 1 cops should not be enough to surround the robber. Maximum degree should be 3. So we take some base graph. This is just example picture. So it should be some 2k regular graph. So k will be a power of 2. 2k regular graph of girth at least 5 for technical reasons. So no 3 cycles, no 4 cycles. And it should have k orientation. I mean, every 2k regular graph has a k orientation. So you divide, so you orient the edges so that every vertex has k outgoing edges and k incoming edges. Okay. And then we have parameters, and the parameter s here, this is basically log k. This is the height of this tree that I showed you. These are going to be the trees. So think of s as being small. Yeah. And then we have some long paths between vertices. So every vertex of my regular graph has k outgoing and k incoming edges, which I split into these trees with k leaves each. 1 for the outgoing edges and 1 for the incoming edges. And then the original edges of my base graph H will be replaced by very long paths. And think of L as being really, really long. Yeah, nowhere near S. Okay. So S is small and L is large. And now I do this for my base graph, and I do this actually twice. I take 2 copies of the same base graphs. And then for every edge, which is now a long path, there is like 1 middle edge of the path. So the path has like an odd length. And for the middle edge, I actually identify these vertices, these edges. So between the 2 copies, H1 and H2, there's lots of identifications, always 1 corresponding to 1 edge of the base graph. Okay. And now I add, for every original vertex of copy 1, I make a cycle of exactly how many vertices there are in H. And the number of vertices in H is more than S. Yeah, it's more than the degree of H, but still very small, smaller than L. Yeah, I choose L even larger. And I make these, so this is just a cycle in any order, no particular vertex ordering here. And I make these connections into the copy 1 by, again, long paths. So long M, medium long. So way more than the length of the cycle up here, way more than S, but way less than L. Okay. So way less than L means, for instance, I can go, instead of going here, this is like distance L. Going M, cycle M is way shorter. Okay. All right. So now, maximum, this is the entire construction. Maximum degree 3 should be clear. Question is, why are 2 cops sufficient to catch the robber? Here's a strategy for 2 cops. They start on the cycle. If the robber also starts on the cycle, they first try to get rid of him from the cycle. They try to push him down to H1. Yeah, you remember that on a cycle, 2 cops are enough to capture him. So they just perform the strategy on the cycle, go towards them. Actually, 1 cop can just stay where he is, and the other cop just moves along the cycle towards the robber. So if the robber decides to stay on the cycle, he will be caught. So at some point, he must go down. Yeah. Going down, he might go up again, come back to the cycle, but the cycle is short compared to the length of this path here. So at some point, he is so far down the cycle, so far down here that it's more than the length of the cycle. So he's really committed. Yeah. And at this point, the cops can reposition themselves on the cycle to be on the same vertex where the robber is still on the way down, yeah, because it's so low. Okay. Now, the robber is in H1. If the robber chooses to, well, 1 cop is just going after the robber, forcing him to continue to move. So he chooses to go into one of those vertices and then along one of those edges. It might be an incoming or an outgoing edge, I don't care. Some edge. And he might also come back, but 1 cop is just going after him, for making him, forcing him to make a decision on which edge to go. The other cop just stays up there and waits for this decision to be made. If the decision is made in the sense that they are both now on this path, which is so long, this cop has enough time to go to the other end of this edge. Yeah. He is on the other end of this edge. Now the effect is that the robber, if he's not caught, must go to the second copy. He cannot stay in the first copy. Yeah. So at some point he must go to the second copy, and either he goes like this or he goes kind of around like this. But in any case, at some point he will be on a vertex where the corresponding duplicate vertex in H1 has a cop. Yeah. And now this cop just stays always on the duplicate H1 vertex of the robber vertex. So he just mimics the cop, the robber moves in H2, he mimics in H1. And the cop that doesn't mimic, this cop just goes after the robber, forcing him to move. So I don't know, the robber does something here and this cop mimics the same thing here. And this cop just goes after the robber, making him forced to move, but making him forced to move also makes him use one of those shared edges at some point. Because without the shared edges, the graph is just a forest down there. So at some point, he's forced to use this shared edge, and then the copying cop is going to catch him. Yeah. Okay, so this way, that's why 2 cops are enough. So why k cops are needed, so k minus 1 cops are not enough to surround the robber. I have to give you a robber strategy. In the robber strategy, I just give you, so here's again the construction a little bit in less detail. Robber just stays on H2. Yeah. And let's assume that the cops are all in H1, but there might be also cops in H2, of course. Yeah. And the robber always is at the vertex here, and now wants to find a new vertex in H2 that he wants to go to. So he wants to find one outgoing edge to another vertex in H2. He has k choices. There's only k minus 1 different cops. So somehow there is one of his k choices which is not where there's not a cop waiting for him, kind of. Yeah. So not on the way and not in the proximity of this target vertex. Yeah. Cops in H2 are not really a threat for him, but cops in H1 might be, because cops in H1 might guard several of his k possibilities by being in the respective copies of H1. And now we're playing the game as before. He can, by always looking up where the cops are here and where there's fewer cops, making his decision, he can find a safe spot to stay in H2, kind of thing. Yeah, very rough, but I hope you might have an idea of why this should work. Okay. So let me just show you this slide once again. I talked a lot about this surrounding variance and that they are basically all the same, well, up to constant factors or factors of delta. But they are very different from the classical variant. Yeah, so the classical cop number can be much smaller than all these surrounding variants. So it's sometimes the case that you can catch the robber quite easily, but surrounding him is very hard. In the end, let me just tell you one more variant, but I'm not going to show you any more proofs. Just one more variant. So I'm always interested in planar graphs. So of course you can do all this on planar graphs, and then there's interesting questions. But this is just a special kind of graph class where you can ask certain things. So for instance, it's well known that for planar graphs, the classical cop number is at most 3, but the surrounding cop number can be arbitrarily large. So I showed you the stars, for instance. Yeah. But I want to show you a variant that really uses planarity in a different way, which is surrounding face variant, because why not? Right? So if we have cops on vertices and we have cops on edges, so why not having cops on faces? Yeah. Same rules, just that the board now is a planar graph with a fixed plane embedding. Robber is not changed. He occupies vertices and he moves along edges, or he stays put in his turn. The cops change and they now occupy faces, and they move across edges. So basically the cops move on the dual. Yeah. And of course, the robber should be surrounded if cops are on all the incident faces of the current robber vertex. Yeah. You can also think about the catching version here. So if a cop is just incident to the vertex of the robber, but this doesn't really change much. It's basically the same as the classical game. So the surrounding vertex variant is quite interesting. Okay, so let's play the game. So here, for instance, my favorite graph again, and 3 cops, and they occupy these 3 faces. So seeing this, the robber chooses to be there, and then the cops' turn, they might do something like this. Now you can also think about a restricted variant where the robber should not be allowed to go here, or he is. It doesn't matter too much. So say the robber moves there. Yeah. And now the cops can do this and surround him. Okay. So in particular, in this graph, I claim if you do a corresponding C sub f of G in this particular plane graph, 3 cops are sufficient. You would have to prove this. And but on the other hand, 3 cops are also certainly necessary because every vertex here has degree 3, right? So every vertex not only does it have degree 3, it is also incident to 3 distinct faces. So just staying, if there's only 2 cops, just staying on any vertex is just fine, and you defend against 2 cops. Okay, so so the face cop surround variant of this graph should be 3. So we wondered again what happens in terms of the maximum degree. Okay, so we want to compare what is maximum degree of the graph and the largest cop number among all plane graphs with this maximum degree. Yeah, so you can start by thinking about maximum degree 1. And it's easy that indeed 1 cop is necessary and also sufficient. Then maximum degree 2. Yeah, so it's always the primal graph. So it's a bunch of cycles in a plane embedding. And then it's also easy to see that 2 cops are necessary sometimes and always sufficient. It's not so hard. The first non-trivial case is maximum degree 3, where indeed we can prove that 3 cops are sometimes necessary and always sufficient. And it's actually quite a beautiful proof. Then maximum degree 4 gets a little bit more complicated, and the answer is 6. Yeah, so 6 cops are always sufficient, but also sometimes necessary for maximum degree 4 graphs, plane graphs. And maximum degree 5, it's actually unbounded. So there is planar graphs, plane graphs with fixed plane embeddings on maximum degree 5, where the number of cops that you need to surround the robber to even come close to the robber is unbounded, and quite a nice construction there. So yeah, that's all that I wanted to tell you. I hope you learned a little bit, and you're also liking cops and robber games as much as I do. Thanks.